Prototyping in the design phase is the process of creating an early, simplified version of a product, service, or process to test ideas before full-scale implementation. The purpose of prototyping is to validate design assumptions, check functionality, and gather feedback early when changes are faster and less costly. Prototypes can be physical models, digital mock-ups, simulations, or pilot processes, depending on the industry. By building and testing prototypes, teams can identify design flaws, usability issues, and performance gaps, refine requirements, and ensure the final design meets customer expectations and CTQs. In DMADV, prototyping reduces risk, avoids costly rework, and builds confidence that the design will perform effectively in real-world conditions before moving to full deployment. Rapid prototyping is the process of quickly creating a preliminary version of a product, service, process, or system to test its functionality, behavior, and user experience. This prototype is not the final product. Instead, it serves as a test version that allows teams to gather early feedback, identify issues, and refine the design. By testing ideas at an early stage, rapid prototyping helps reduce risk, save time and cost, and ensure the final design better meets customer needs and performance expectations. Physical prototyping is a type of rapid prototyping mainly used in manufacturing, hardware, automotive, and medical device industries. It involves creating tangible models such as 3D printed parts, mock-up packaging, printed circuit boards, car dashboard foam models, or sample machine tool blocks. These physical prototypes allow teams to test fit, form, function, ergonomics, and manufacturability early in the design phase, helping identify issues and refine the design before mass production. Physical prototyping helps test critical aspects of a design such as shape, size, and ergonomics to ensure it is comfortable and practical to use. It also verifies proper fit and assembly between components, checks physical strength and durability, evaluates safety under real conditions, and supports correct material selection before moving to full-scale production. Digital prototyping is mainly used in IT, software, applications, BPO workflow automation, and UI/UX design to quickly test ideas in a virtual environment. Examples include wireframes, clickable app prototypes built in tools like Figma or Adobe XD, simulation dashboards, AI or ML model prototypes, CRM screen mockups, and process models created in BPM tools. Digital prototypes help test user experience, navigation flow, logic correctness, system and IT integration, and performance estimation, allowing teams to refine the design early and avoid costly rework later. Rapid prototyping is important because it enables early detection of design flaws when changes are easy and inexpensive to make. It significantly reduces the cost of rework, improves customer satisfaction by incorporating feedback early, and helps stakeholders clearly visualize and understand the design. By speeding up approvals and development cycles and validating feasibility before investing in full-scale implementation, rapid prototyping reduces risk and increases the chances of design success. Rapid prototyping is important because it enables early detection of design flaws when changes are easy and inexpensive to make. It significantly reduces the cost of rework, improves customer satisfaction by incorporating feedback early, and helps stakeholders clearly visualize and understand the design. By speeding up approvals and development cycles and validating feasibility before investing in full-scale implementation, rapid prototyping reduces risk and increases the chances of design success. Piloting begins by clearly defining the pilot scope, which includes deciding which part of the process or design will be tested, how many customers or users will be involved, the duration of the pilot, and the resources required. Once the scope is set, the pilot is executed by running the design in real operating conditions, closely observing how it is used, and systematically collecting data to evaluate performance and identify issues. After the pilot is executed, performance is measured using key KPIs such as cycle time, defect rate, reliability, user satisfaction, and cost efficiency to evaluate how well the design performs in real conditions. Feedback is then collected from customers and users, operators, maintenance teams, and supervisors to understand practical challenges and improvement opportunities. Based on this data and feedback, iterative refinements are made by fixing bugs, improving layouts, adjusting workflows, reducing unnecessary steps, enhancing user experience, and adding or removing features, ensuring the design is optimized before full-scale implementation. In a manufacturing context, piloting and iterative refinement help validate the design before full-scale rollout. For example, when a new automated packing line is designed, the pilot may be run on only one shift instead of 24-hour operation. During the pilot, issues such as sensor misalignment causing to percent packing errors, high operator adjustment time, and slightly longer cycle time than predicted may be observed. Based on these findings, refinements are made by correcting sensor positions, adding a jig to hold packets properly, and providing targeted operator training, ensuring the system performs reliably before full deployment. In a BPO or service environment, piloting a new customer email workflow may involve running it with only 10% of the total email volume, a selected group of agents, and limited operating hours. The pilot can reveal issues such as auto-tagging errors, the need to improve the tone of email templates, and SLA achievement reaching only 94% against a 98% target, leading to refinements in tagging logic, content design, and workflow rules. In an IT example, a new customer mobile app prototype tested by 50 beta users may uncover problems like app crashes at the OTP page and confusing navigation, resulting in refinements such as bug fixes, improved flow, and the addition of a tutorial page to enhance usability before full launch. Even if a design functions perfectly, it must also be financially viable. Financial analysis ensures that the design delivers real value, that the benefits outweigh the costs, and that the long-term return on investment ROI is justified. This evaluation provides management with the confidence to approve full-scale implementation, ensuring resources are allocated to solutions that are both effective and economically sound. Financial evaluation ensures that a design is not only effective but also economically viable. Cost-benefit analysis compares the required investment, including tools, manpower, training, and licensing, against expected savings from improved quality, higher efficiency, and reduced waste. Return on investment ROI, calculated as the net benefit divided by total cost, indicates the profitability of the design, while net present value (NPV) measures future cash flows discounted to today's value, with a positive NPV confirming that the design is financially worthwhile. Together, these metrics help management decide whether to approve full-scale implementation. Additional key financial metrics include internal rate of return (IRR), which represents the rate at which a project breaks even, with a higher IRR indicating a more attractive investment, and payback period, which measures the time required to recover the initial investment, where a shorter payback period reflects a more favorable and quicker return. Cost considerations in prototyping cover multiple stages. Design costs include engineering, software development, and material trials needed to create the initial prototype. Pilot costs involve limited production, training, temporary setups, and monitoring expenses to test the design under real conditions. Implementation costs arise during full-scale rollout and include machine or system setup, IT integration, hiring and training staff, and managing organizational changes to ensure smooth adoption of the new design. The benefits of prototyping extend beyond design validation and include tangible cost savings and performance improvements. By refining the design early, prototyping helps lower scrap, increase productivity, reduce defect rates, enhance customer satisfaction, decrease costs associated with SLA breaches, and minimize manual work through automation, ultimately providing both operational and financial advantages. For example, in manufacturing, a new filling machine requires an investment of 40 lakh. Expected annual savings include 12 lakh from scrap reduction, 16 lakh from lower labor costs, and 6 lakh from reduced warranty claims, totaling 30 lakh per year. Calculating ROI as 3440, 40 gives minus 15% in the first year, while the payback period is approximately 1.2 years. Despite the initial negative ROI, the short payback period indicates that the design is financially viable and worthwhile for implementation. For example, in ABPO, an automated email routing system requires an investment of 6 lakh. Expected savings include 12 lakh per year from FTE reduction and 4 lakh per year from reduced SLA penalties, totaling 16 lakh annually. The ROI calculates to 166%, and the payback period is just 4 months, making this a very strong and financially compelling business case for implementation. Rapid prototyping allows teams to quickly create a test version of a design, whether physical or digital, so potential issues can be identified and addressed early, saving time and cost. Piloting takes this a step further by testing the design on a small scale in real operating conditions, validating performance, and ensuring that critical to quality CTQ requirements are met before full implementation. Iterative refinement involves using feedback and performance data from prototypes and pilots to repeatedly improve the design, removing flaws and stabilizing the process or product. Finally, financial analysis evaluates the cost, expected savings, ROI, and payback period to confirm that the design is economically viable and justify approval for full-scale rollout.